So a wormhole in reality is something that the laws of physics allow.
Quantum computing has the potential to change computing world on a massive level.
Most people are aware by this point that quantum computing is a game-changing piece of technology that exploits some of the more peculiar properties of quantum mechanics in order to solve specific tasks at a rate that is significantly quicker than traditional computers. These issues vary from mathematics to retail business and from physics to finance. If we master quantum technology, the gains should benefit the entire economy and boost competitiveness. But can these quantum computers be used to solve the universe's mysteries? There are numerous mysteries in space that scientists are seeking to solve, and in order to gain a deeper understanding of these mysteries, scientists are daringly attempting to duplicate them in the lab using cutting-edge technology. Like how they created a wormhole using Musk's Neuralink AI computer, then quickly shut it down. What were these scientists hoping to accomplish with their experiments, and how can a wormhole be generated with a quantum computer? Stick around till the end to know all the shocking details of this experiment. A wormhole is a special solution to Einstein's general theory of relativity equations that creates a tunnel between two distant points in space or time. The concept of a wormhole emerged soon after the discovery of the first exact, non-trivial solution in general relativity, the Schwarzschild solution, which corresponds to a non-rotating black hole. To obtain this solution, all you have to do is take completely flat, empty space and place down one object of infinitesimal volume but finite mass. Wherever you put that, you'll have a black hole with a specific mass surrounded by an event horizon with a radius determined by that mass. In late 1915, Einstein completed general relativity, and in early 1916, Carl Schwarzschild published this early, amazing solution, which is still relevant and frequently used today. However, scientists never discovered a way to keep a stable wormhole in the universe until Musk's quantum computer came along. But where do wormholes come from? In 1935, Albert Einstein and Einstein-Rosen found the simplest conceivable wormhole solution, which is why wormholes are also known as Einstein-Rosen bridges. Einstein and Rosen started with a mathematical solution to the problem of a black hole, which consists of a singularity, which is a point of infinite density, and an event horizon, which is a region surrounding their singularity beyond which nothing can get away. They observed that they could extend this approach to include white holes, which are the polar opposite of black holes. These hypothetical white holes, like black holes, have a singularity, but they work in reverse, with nothing entering the white hole's event horizon and any material inside the white hole being ejected immediately. Einstein and Rosen discovered that every black hole is theoretically associated with a white hole. Because the two holes are in separate positions in space, they are connected via a tunnel or a wormhole. Whether or not wormholes can physically exist or not is a question that's still hotly debated. Yes, we can mathematically write down solutions to Einstein's equations that include them, but mathematics is not the same as physics. Mathematics tells you what's within the realm of physical possibility, but only the actual, real universe itself is going to reveal to you what's physically true. The places we'd look for such physical evidence have all come up empty so far. But what do you get if you combine wormholes and quantum computing? Quantum computing has altered the world, altering fields as diverse as communications, AI, and health. Moreover, Google has announced that their quantum computer is superior to classical computers, a significant milestone in the development of quantum computing. So what is quantum computing and how does it operate? Standard computer chips employ bits, which are analogues to tiny switches that can be in either the off, represented by a 0, or on, represented by a 1 position. Millions of these bits in various configurations of 1s and 0s make up every program you use, every website you visit, and every picture you snap. In quantum computers, bits are replaced by qubits, which can be in a variety of states beyond simply on or off, including a continuous spectrum. If you give a standard computer the task of navigating its way out of a maze, for instance, it will go down each branch, eliminating them one by one until it finds the exit. A quantum computer can traverse the maze simultaneously. Entanglement is another property of qubits. Ordinarily, the outcome of one coin has no influence on the outcome of the other. They are independent. Entanglement happens when two particles are physically separated yet are linked together. If one comes up heads, the other will as well. Next, let's go into how wormholes and entanglement are interconnected. How two black holes entangle with one another was of interest to physicists Juan Maldacena of Princeton's Institute for Advanced Study and Leonard Susskind of Stanford University. It is assumed that entanglement takes place between extremely small particles rather than between enormous cosmic bodies. However, Susskind and Maldacena proposed a connection between entanglement and wormholes because they reasoned that if two black holes were entangled and then separated, the result would be a wormhole connecting them. Since then, other research groups have agreed that their theory convincingly shows that entangled quarks are connected via a wormhole in a simplified reality. This concept postulates that the wormhole can be found in our 4D universe, which consists of 3 spatial dimensions and 1 temporal dimension. This is like using a 2-dimensional hologram to portray a 3-dimensional object when the quarks are only coupled in a flattened 3-dimensional replica of reality. This means that wormholes can be found anywhere entanglement occurs. They went so far as to characterize the two as ER equals EPR, where ER is an Einstein-Rosen bridge or wormhole, and EPR is short for Einstein-Podolsky-Ross, which is another term for entanglement. Wormholes have also been demonstrated to exist by Harvard's Daniel Jafferis, Ping Gao, and Stanford's Aaron Wall. Finding a technique to create a wormhole through which light may travel was a huge step forward in the pursuit of a quantum gravity theory. The fundamental relevance of this finding can be found in its application to the black hole information dilemma and the connections between gravity and quantum mechanics. Jafferis's thoughts on two quantum entanglement black holes, as formulated in Maldacena and Susskind's ER equals EPR correspondence, influenced the new theory. Despite the fact that this means that the direct connection between black holes is shorter than the wormhole connection and thus wormhole travel is not a shortcut, the theory provides fresh insights into quantum mechanics. Jafferis's idea is based on Einstein and Rosen's setup, which consisted of a connection between two black holes. The wormhole was a specific scenario in which information could be recovered from a black hole because it was traversable. It offers a causal probe of regions that would otherwise be concealed behind a horizon, as well as a window into the experience of an observer inside a visible from the outside space-time. To date, the demand for negative energy, which is believed to be incompatible with quantum gravity, has been a major barrier to building traversable wormholes. Jafferis, on the other hand, has addressed this by calculating quantum phenomena analogous to the Casimir effect using quantum field theory techniques. If you're wondering what negative energy is, consider this. The gravitational potential energy that keeps two particles of matter together must be negative because it requires positive energy to separate them. Given a nearly uniform universe, the whole negative gravitational energy in it would exactly cancel out the total positive energy represented by matter, resulting in no overall energy for the universe as a whole. Scientists, on the other hand, have created a wormhole in the laboratory for the first time. According to researchers, the effort is a step towards a bigger program of testing quantum gravity theories with a quantum computer. The current work looks into the quantum teleportation equivalence of wormholes. The initial tests were undertaken by the Caltech team to investigate the hypothesis that information moving from one point in space to another can be expressed using either wormholes or quantum entanglement. Alexei Kateev, a Caltech professor of theoretical physics and mathematics, demonstrated in 2015 that a basic quantum system can display the same duality later described by Gao, Jafferis, and Wall, such that the model's quantum dynamics are equal to quantum gravity effects. This Sachdev-Yi-Kateev (SYK) model led academics to propose that some theoretical wormhole notions may be examined further by undertaking quantum process experiments. This type of experiment was carried out for the first time in the current study by a team of scientists who employed a baby SYK-like model that was built to retain gravitational features and observed the wormhole dynamics on a Google quantum device, the Sycamore quantum processor. This suggests that it is not just Musk who is working with wormholes. Google is much ahead of Musk in their research. To accomplish this, the researchers first had to reduce the SYK model, which they performed using machine learning methods on common computers. They employed machine learning approaches to discover and build a small SYK-like quantum system that could be encoded in current quantum architectures while keeping gravitational features. To put it another way, they simplified the microscopic description of the SYK quantum system and studied the resulting effective model on the quantum processor. It was exciting and surprising to see how the optimization of one model feature preserved the other measurements. They plan to run additional experiments to acquire a deeper grasp of the model itself. The experiment was performed by putting a qubit into one of the researchers' SYK-like systems and then monitoring the resulting information flow in the other. The information was transported from one quantum system to another by quantum teleportation, or in gravity's complementary language, through the traversable wormhole. As a result, they were able to create a wormhole-like quantum teleportation. To accomplish this, they had to simplify the quantum system to the simplest example that still kept gravitational features, which they then implemented on Google's Sycamore quantum processor. Even though it took a long time to get there, the researchers were pleasantly surprised to find that the gravitational viewpoint provided a straightforward explanation for many puzzling occurrences associated with quantum particles. The latest experiment was perhaps most interesting in that they were able to make the system simple enough to replicate an existent quantum machine using machine learning while preserving a good caricature of what the gravitational picture indicated. In their research, the physicists reported the wormhole behavior predicted by both classical and quantum theories. While quantum information can be communicated or teleported in a variety of ways, the experimental method was proven to be at least somewhat analogous to what would happen if information passed through a wormhole. Let us know what you think about wormholes and quantum computers in the comments area below.